Hello, so in today's video, we're going to look at summing a convergent geometric series. So we're going to look at how we sum convergent geometric series. So let's say we've got a geometric sequence, so A1, A2, A3, A4, and so on and so on. Is a geometric sequence with a first term of A and a common ratio of R, which is less than 1. So remember we said in the previous video that if the common ratio is less than 1, then it means the series, the sum of a geometric sequence, is convergent to a fixed number. So the question is, what if we sum this convergent geometric sequence, well, this convergent geometric sequence and series? What if we sum this up to infinity? So what if we sum every single number in this sequence? What is going to be our answer? How do we calculate that number, that convergent number? So let's remember that if we've got a geometric sequence, so some geometric sequence, AR squared, AR cubed, and so on and so on, the sum of the first n terms was given by this formula here. So the first term times 1 minus the ratio to the power of n divided by 1 minus r, that was the sum of the first n terms. If you wanted to find the first 10 terms of a geometric sequence, your first term would be the a value times by 1 minus the common ratio to the power of 10 divided by 1 minus common ratio. That's how we found the sum of first n terms. But now we've got a convergent geometric sequence. We want to find out what is the sum to infinity. So if we actually make this basically infinity here, what is going to be our sum? What will our formula be for a convergent geometric sequence? So let's look at our formula again. So a geometric series is convergent if and only if the common ratio is less than 1. So that's what we're saying. So if you've got a common ratio of 0.5 or minus 0.5, anything with an absolute value less than 1 and modulus less than 1, the series, the sum will converge to a number. And the objective is, can we use this formula to find out what that number or what the formula would be? So let's think about this. So if n, this number here, which we want to be massive, if it is a large, massive number, and if this r value has a size less than 1, then that means that r to the power of n is about 0. So think about it. If you pick r equals 0.5, for example, well, 0.5 to a massive number, that's going to go basically close to 0. So the idea is that if you do pick a value of r less than 1, or a value of r between -1 and 1, raise that to a power of a massive number n, it's going to be about 0. So let's think about this. That means that the limit as n tends to infinity of r to the power of n is equal to 0. So you've got a common ratio with a size less than 1. That means that that number to the power of a massive number is going to tend closer to 0. So the limit is going to be 0. So that means if we look at our sum formula, this formula up there, the limit of our sum as n gets closer to infinity, well, that's going to be the limit as n gets closer to infinity of the fractional formula that we had. So what we can do with these limits, when you take limits, you can actually just split up a fraction. Sorry, I forgot to put the a there. Sorry, there should be an a there. So when we expand the brackets, we get a, take away a r to the power of m. I'm just writing that here. So we're going to split the fractions too, and we're going to take limits of both fractions. So when you take the limit as n tends to infinity of this first fraction here, well, there's no n involved. There's no variable letter n in this fraction. So that's just that number there. So we get this a over 1 minus r there. Now take away the limit as n tends to infinity of this number here. Well, as we just said up here, when n tends to infinity, if you have a ratio between -1 and 1, this is going to tend to 0. So you're going to get a number getting closer to 0 on the top of the fraction. A fraction with 0 on the top is 0. So basically, this second fraction is going to tend to 0. So this limit is going to be equal to 0. So we've got this fraction take away 0. So the limit is going to be a divided by 1 minus r. So basically, if you've got a convergent geometric series, so a plus ar squared plus ar cubed plus ar to the power 4, and so on, where r is between -1. So remember, this just means that r is between -1 and 1. That means your sum will be a divided by 1 minus r. So here we go. So for a geometric series with a first term of a common ratio with a size less than 1, a plus ar squared, so on and so on, up to infinity. Sorry, this is incorrect. Let me put infinity there. The sum to infinity for infinitely many numbers is going to be a divided by 1 minus r. And that's the formula that you need to know. So let's look at how we can apply this formula. So let's say we want to calculate this sum here. So 20 take away 16 plus 12.8 take away 10.24 plus 8.192 and so on and so on and so on. How are we going to calculate this sum? Well, let's look at the sequence of numbers we got. So we got 20 minus 16, 12.8 minus 10.48, minus 10.24 and 8.192. So this is a geometric sequence. So every time, what you may notice is that every time we increase, we go to the next number in the sequence, we're multiplying by negative 4/5. So we're timesing by negative 4/5 each time, negative 4/5, negative 4/5. So we've got a common ratio of negative 4/5. So that means the common ratio is negative 4/5. And we got a first term in our sequence of 20. So our first term is 20. So that means the infinite sum, the sum to infinity of this geometric series. So obviously this is a geometric sequence here. So this sum is a geometric series. We've got a geometric series. So geometric series. So the geometric series is going to sum up to the infinite geometric series is going to be using our formula. So the first term, which is 20, divided by 1 minus the ratio to 1 minus 4/5, which is just going to be, so 4/5 plus 1, which is basically going to be 20 over 9/5. And that's going to give us 20 times by 5/9. So basically 100 divided by 9. And that would be our final answer. So this sum there, when you keep on summing all these numbers in this sequence forever and forever and forever, the limit, the sum is going to be 100/9. That's going to be the infinite sum for this sequence here. So that's just an example of how we can use the formula a over 1 minus r to calculate a geometric series, the sum of an infinite geometric series, when the common ratio has a size less than 1, and so when the sequence is a convergent geometric sequence.